Okay, earth science time. Already messed up. Earth science time. Today we're talking about groundwater. Can you guess where this water is? A+. You get a ramrock. In the ground. This is, let's break this down. This is water from in the ground. We're having a good time though. The objective for today, as you probably already wrote down because I just told you to, is to relate surface and groundwater. So it's a little bit more in depth than just water, what is in the ground. And there's a lot, to be real, to play let's get real here, folks. There are a lot of misconceptions about this, okay? It's nowhere near as simple as just water that is in the ground. Relate is the objective. Earth's surface water to its groundwater. Remember, if you are in earth science, that you have lesson self-checks and a worksheet due on Friday, so you should be working on those. And hopefully, the content of this lesson will help you with that. Remind me, what do we call the collection of all of the water on Earth? What do we call that? You remember? When we think about all the water on Earth, we call it the what? That collection, the hydrosphere. And this includes the groundwater. The hydrosphere is, my text tells me, the hydrosphere is about 97.2% what? Can you guess? What is probably 97.2% of the hydrosphere? Yeah. The ocean. Another 2.15%. Give me another guess. What's probably the second most common location for water to be in the hydrosphere? Yeah, exactly right. Glaciers, or the book also says ice caps, but that just means the permanent glaciers, or hopefully more permanent than we're worried they are, glaciers in the North and South Pole, the Antarctic and Arctic circles, irrespectively. Next, what's the next most common, do you reckon? 0.31%. Yeah, actually, other than this one, these are all going to be fresh water, what we call fresh water, meaning that it's more or less pure water. All water on the planet, unless we specifically intend for it not to, has some dissolved salts, some dissolved what we might call minerals in nutrition. We can distill water to remove those. We can deionize water to remove those, or to remove many of them. But all of them have some, but the ocean has a much larger amount than the others. But these are all what we call fresh water, even though they still are not pure water. What do you think? Where's the next highest amount?
Aquifers.
I'm glad you used that word. I was going to use the word groundwater. But they're not exactly equivalent, but they are so neatly related that we can put them both in as the place there. Next. Sorry, I have to actually know the percentage. 0.009. Oops, that's not a 9. That's another percent sign. Percent. 0.009%. What do you think is the next most common? It's going to be kind of fresh water. We already said that. Guess. Where might we find 0.009% of the rest of the water? Lakes. Good. I'm glad you said that one first because a lot of, oh, actually, look at it. Check this out. Ta-da! It actually is really good. Looking at this, you can see a little bit of a, don't worry about that. Actually, it turns up great on camera, though. You can see, what is all that? What is all the blue up here? Water, ocean water. So far does that make sense? The 97.2% of all the blue we see up here, it wouldn't be exactly 97.2 because the next most was groundwater, right? We don't see that. That's within the ground. As we already said, remember, groundwater is that water in the ground. Don't forget that. But you see also some blue over here. These are actually technically lakes. Some blue over here, some blue up in here. And all those blueies are lakes. What's the next one going to be before I pull this back up? That you see much less blue of, barely any actually, rivers. Oh. There she goes. Okay, don't worry about it. The next one, these two are about tied, 0.0001% and 0.0001%. Rivers, and then where's the rest of it in the hydrosphere? In the atmosphere. There's kind of I don't know, a glaring missing thing in here. Where else is there water in the hydrosphere that isn't up here? It actually isn't going to be one of these percentages. It kind of seeps in the cracks of all of them. Where else is there water? You are so good at this, Peyton. Where are you getting this from? Not just human bodies, but all the bodies of all of the creatures worldwide. Plants, animals, all of those actually make up a very, very little bit, about this much again. So let's put that again, about 0.0001% in the biosphere. Now, whether these all add up to 100% or not, I do not care. This is not math. This is not the quadratic formula. Don't at me. Whatever they add up to is what they add up to, but these should be right because I got them from the table. So the hydrosphere takes the form of these many different things, but it's all water. It's all the water on Earth's surface. And today we're going to focus on this one. I'm really glad you used this word already, Peyton. Aquifer. Let's break this word down. This will be a little bit better than the last one because while that one was a compound English word, this one is a compound Latin word. And so what's aquifer probably mean? Okay, yeah, the aqua part you're recognizing. Aqua comes from the Latin for water. Do you know what fur is from the Latin for? Fur. Have you ever met someone named Christopher? Christopher is someone who furs Christ. Have you ever heard of a metaphor? A metaphor is something that furs across a point. Meta meaning across. Can you guess what fur might mean? Let me think of another example that has fur in it.
Mr. Grizzle has fur.
That's F-U-R. But he does fur, if we're going to use the Latin. Can you guess now? I mean, that's not how anything has. Yeah, just carries, actually, is what it is. It's carries. Water, we might use the word bearing or carrying. The point is that the noun here, the aquifer, is not the water itself. It's something that is doing what with the water? Carrying it. It's holding it, we might even say, would be better, maybe. Holding. And what is it? What's the actual noun here? What is doing this water carrying? It is always, and at least as we use it, aquifer is always a what? What's the noun here? The implied noun, since we're talking about earth science. It's what that bears water. What that carries water. Almost. I mean, yeah, I'm not going to write that word, but you're right. It's what? What substance? Almost, but I'm not going to write that. Help him. Almost, but I'm not going to. We're orbiting the right answer. We're orbiting what I want to write.
It's not the biosphere. It's not aquifer.
No, it's the geosphere. It's the geosphere. What am I going to write? What's the noun for this? What is carrying this water? He said ground. Maybe you said ground. He said dirt. Earth. We're orbiting it. We're getting at what I actually want to write down. Rock. Who said it? Ramrock. Who said it? Nice job.
I did.
Was it you, Josie? Rock. We're talking about a rock that bears water. That's what an aquifer is. So when we talk about an aquifer, let me tell you this. This is one of the main misconceptions I want to point out. When I was a kid, and not even like a young kid, like until I was maybe out of high school, maybe even until I started learning about earth science at a college level, I thought that aquifers were like that level from Mario where you just fall down a hole. Like here's the ground, and there's a hole in the ground, and down here is basically like a bottle of water. And there's like some stalactites and stuff in it, and this is an aquifer, just a hole in the ground with water in it. It can be that way, but it's not usually. Usually, aquifer is a layer of rock. What kind of rock am I indicating here, geoscientists? You should know this. We've done this all year long. What do the little dots mean on the rock? What kind of rock is that? I'm looking at the wrong people. Josie and Wes, you are not responsible to know this. Tegan, no, you don't have to know this. What kind of rock has the little dots? What? What did you say? What did you say? Say it to the... It's a stone.
Oh, sand? Sandstone.
Yeah. Sandstone. And you have no idea how embarrassed that person just got because of... So what happens is... Now what's he drawing? Say it. Say his real name. Now what's he drawing? Say the real name. Oops, I ran out of room. Infiltration. This is a very simple, but I think pretty good drawing of what goes on. What must be true for this rock to allow the water to infiltrate? Does all rock allow infiltration? No. It has to be not just porous. Absorbent in yellow and porous here. Remember, that rock can be porous. These are indicating holes, what we sometimes call vesicles. In fact, there's a kind of rock that we encounter sometimes. You might have used this on your feet called pumice that has these vesicles in them, these holes in them, but it is porous. Absorbent in yellow and porous is he, but it is not this other word. Where imagine I'm drawing a lot of sand particles. You remember this from your lab. There's just sand here, right? This one is, the pumice was porous. This one, though, is permeable.
So it has to be both.
It has to be. All permeable rock is porous, meaning that it has pore spaces. But not all porous rock is permeable. Permeability is the ability for water not to only be in a pore, but to move from one pore to another. Permeable. It can permeate. You might remember from biology that a cell has a semi-permeable membrane, meaning some things can pass through it and some things can't. Semi-permeable. Some can go through, some can't. Permeable means it can go through. Permeable means it can go through. So this sandstone here is permeable, meaning that whatever water comes down can go through the pore spaces and eventually end up down here. Now, what's this line represent? Because if this wasn't here and it went down forever, can that be possible? Can I just have sandstone all the way down? No. Why not? Eventually it'll get what? What's down, down, down? Yeah, eventually it would either melt or deform so much that there's no more air spaces. And the pressure would get greater, wouldn't it? And so we end up having usually layers of this permeable rock called an aquifer because it bears water. Let me erase the misconception. Permeable rock, which is an aquifer. And it's usually underlain. That means that it's underneath it. That what's underneath it is some kind of impermeable rock. Here I'm drawing shale. Impermeable. Maybe spelled wrong. Might not be two M's. I don't think there are. Impermeable rock, which we call, do you know, I think it was one of your vocab words. This is an aquifer because it bears water. What might this be? What do you think is going to be the root word of this too? Aqua. It's going to have to do with the water. But instead of bearing the water, aquifer, it excludes the water. We call it an aquiclude. Aquiclude. So the water infiltrates down and fills in the pore spaces to a certain level downward, and then it goes no further. Why? Because this rock below doesn't have the pore spaces necessary for that to occur. And this interface between them is called this line, where above it, there are pore spaces up here, but the water is just seeping through. What are these full of generally when they're not being infiltrated? What's in the pores here? Be careful, because you're tempted to say nothing. Is there nothing in the pores up here? No? Air. Yeah, right. Normally, they're full of air. This is why I wanted you, in one people's lab, they had sand in a beaker or a graduated cylinder. They poured water in, and I wanted them to notice the bubbles coming out, because the water, as it permeates, as it infiltrates, is not just going into empty spaces. It has to push out air, and so there's air up here. So the line between which there is air above in the pore spaces and water below in the pore spaces is called the water table. This is an extremely important concept for hydrogeologists. That is, people who study hydro, water, geo, earth, ology, the study of those things. So people who study hydrogeology, people who study the interface between water and earth, love this idea of a water table, because this is the place where we go lower than that, the line where we go lower than that, water is down there. Okay. People like my friend Brian Prosser, who dig wells, love the water table, because that's how deep you have to dig. And the water table varies in different locations, depending on many different things. One other misconception that a lot of people have about groundwater is this. Let me redraw. I'm going to erase these two kind of microscopic drawings. I'm going to draw another drawing here of a hill. This is a good drawing of a hill. I'm here to say this is a good drawing of a hill. If I drew that hill with a curve, why am I drawing these lines straight and flat? You remember the principle of Steno that tells us the answer to this question? What principle is it that these layers are straight and flat, even if the land above them is curved? Do you remember that principle? Original horizontality. Good. You got it. Okay, here's my really good drawing of a hill. Here's my really good drawing of a hill. Is this hill, can you tell, is this hill diagram drawn in cross-section or in map view? Cross-section. This is drawn in cross-section, meaning I'm looking at kind of a cutaway. Now what have I drawn? Label it. What's this line? Kind of like the other drawing. What's this line? Water table. Thank you. You're on fire today, dog. This is the water table, meaning that at least at this time, and at least in this place, above this line, the pore spaces are full of air. Below it, they are full of water. Lower? Could they be full of water down here? Well, the way I have drawn it, no, because this aquiclude has stopped that. But if maybe there's a fault here. This is getting into a little bit of a more complicated. Maybe there's a fault there, and the water can kind of seep down. There can be two water tables in an area. In fact, let me make a little side note here. You're probably aware that there used to be, kind of still is, a uranium mine out yonder. A lot of people have, at different various points in my speaking to, become very worried that the fact that there's a uranium mine that they correctly understand to be the uranium is mined from water. And that's true. That they're worried that because of that, maybe, or maybe for the same reason that mine is there, we all, Crawford residents, are getting poisoned by uranium all the time. But in point of fact, it's actually this. The water that the uranium contains is something like this. We drink water from here, and the water the uranium is here. There's a double water table. That's just a little side note. So don't worry about that. If you were ever worried about that, don't worry about that anymore. But the real point of this drawing that I wanted to show you is the misconception that people have. So if I have, again, my precipitation, if I, again, have my precipitation, and for some reason it's happening only on the hill, I might have even a triple water table here where this water will infiltrate. But check this out. What's going to happen here? Yeah, it's going to run off. And maybe the water table here actually gets higher here and lower here. The water table can follow the curve of the land because the major misconception here is that, and I'm going to write this down, groundwater flows to. Remember we did in the last video a demonstration of, I dumped tea everywhere. You remember this one where I went crazy, dumped tea, it went up and down because I was trying to show to you that water doesn't exclusively flow down. It moves from a place of high pressure to low pressure. And that's the same thing. It's going to become very important in a second when we talk about artesian wells and springs. But in this case, the water is flowing from a higher elevation to a lower elevation underground, just like it does above ground. Okay, because groundwater does flow too. So that's an important thing to know. And when I say it like that, I hope it seems to you like, well, of course it does. It's water, and so of course it flows. But there's a lot of people that are confused about this. So they think that maybe the water in their well is not impacted by things that happen on the surface. Because like the objective says, there is a relationship between Earth's surface water and Earth's groundwater. So check this out. What's this little area right here? I'm going to actually put it in green just so we can kind of see exactly what I'm talking about. What's this thing that I have here in green? It's below the water table, but above the land. What would we call this area? Okay, it might be a swamp. I've drew it in green, so it might as well be a swamp. What else could it be? Could be a pond. What else could it be? Depending on the scale, it could be a lake. If it's flowing, it could be a river. But it's some kind of surface body of water. Yeah? It could be the ocean. It's some kind of surface body of water. Okay? And those two things are directly related. Woohoo! They're directly related. I had too much Celsius. They're directly related. So now I have orange. This is going to be a bad guy. Here's a little boat with a bad guy on it. And the bad guy is dumping poison. Oh, no. He's got his beautiful sailboat, but he's dumping poison. And this poison will flow just like the rest of the groundwater. It'll spread just like it would if I put this cup has only got air in it, but if I had water in here and I put some food dye in it, eventually that food dye is going to spread out. And it's the exact same thing in groundwater. And that's really important to know, that pollution will flow in groundwater just like it does in surface water, and those two things are related. And so not only will he be poisoning thing in the pond, and you could think, like this sounds like a crazy example, but people do this. Like, maybe this is his personal pond. He's got a cabin here. And his pond one day he's like, too much algae, I'm going to poison it all. And he does because he wants his pond to be clean, but it also poisons everything down here. And maybe his well is right here, and then 3 years later he's like, why am I so sick all the time? It's because you poisoned yourself, dog. Do you see kind of what I'm getting at here? It flows too. And it's really easy when the reason this is a hard thing to understand is because it happens underground. Like, the point of it is that it's literally hidden from view. And so he doesn't see the relationship. In a real way, he doesn't see the relationship between this and, why do I feel so sick all the time? He's dead.
I thought you were going to draw him like early hours.
Nope, dead.
It's much worse.
And this is the fumes from his corpse that are also going to seep into the groundwater. Perfect. What was I talking about? Okay, so another thing about wells that you should know. So by the way, this is a well. A well is a man-made, basically a tube that water can flow up into. This over here, if if groundwater is becoming surface water by a natural occurrence, we call this, can you guess what it's called? You probably already know. If groundwater becomes surface water by a natural occurrence, it's called a spring. It's called a spring. So groundwater becoming surface water naturally is called a spring. Groundwater becoming surface water by human means is called a well. And there are different kinds of wells, as Brian Prosser knows. There are different kinds of wells. But all of the times when groundwater is becoming surface water by human means, it's called a well. And when it's by natural means, it's called a spring. Here's some, this is, I think, a beautiful picture. You can pause this, and maybe you can't see it in real life, but this is a nice picture if you pause it of some different kinds of springs. Copyright, Glencoe, 2010, I don't know, whatever, don't at me. I think that's almost everything, except I want to talk about two more things. I did say that I would mention artesian wells and springs. If we change the diagram just a little bit, let me think of how I could do this. If I erase this aquaclude, and I have an aquaclude that does follow the land, right? How could that happen? Remember, we talked earlier about original horizontality. How could it happen that this is not originally horizontal? What force could cause all of these layers to fold as one? When I say all these layers, I mean the sandstone up here, this aquaclude shale layer, and this sandstone down here. What force could cause them all to fold as one thing instead of being cut by erosion? That's what the original horizontality would tell us, that they're laid down flat and then erosion cut this valley. What force could cause it so they all deform like one single lump? Plate tectonics. So maybe there's a tectonic activity, and now this aquaclude, I'm not saying this is a progression of the previous drawing. This is a new drawing. I just used what I already had here. So erase the dead guy. Okay, he's not in it anymore. We got now a valley that was formed by plate tectonics. So if you're drawing these drawings, which I hope you are, if you're in earth science at least, you should draw a new drawing for this. Check it out. I'm going to erase the water table out from here because it can't have water table because it's an aquaclude. So check it out. How many times have I said that in this video? This is getting a little bit ridiculous. The water table, we'll say, is here. Okay, the water table's there. You see what I mean by the water table is there? It's contained there by this aquaclude below. There's some water down there. And there's no water in this layer, we'll say. So what happens if I drill a well, or by natural faulting or something? It could be either a spring or a well. There are both artesian, this is the word I'm using, wells or springs. We'll say that this line here represents either a well or a spring. Either a natural fault or a man-made device that is breaking into, it's going through this aquifer layer that doesn't actually have water. It's going through this aquaclude layer and into this aquifer layer. Well, the water table, you'll see, the water table is actually above, oops, it should be way over here. The water table is above the land in this valley. It's a dry valley, but the water table is above it. As soon as I break into this layer, something really cool happens. Can you guess what? Where's the water going to rise up to? The level of the water table. Have you ever seen, like in Bugs Bunny or something, when Yosemite Sam uses a pickaxe and then oil shoots out? Or maybe like in, what's that? The Beverly Hillbillies, when Judd is shooting up some food and he shoots the ground and bubbling crude comes out, and oil shoots out like this, like a guy, like it just rockets into the sky. Do you know what? Does anyone at all know what I'm talking about? That's because that is an artesian well of oil, not water, but oil. But in those cases where the fluid is reaching some vast height, Maybe it's only a couple inches, but some height above the surface, that's an artesian well or spring, meaning that it's under pressure. And that brings up another thing, that all of this, to at least some extent, applies also to petroleum geology. That the main things that we find in the pore spaces, there are three: air, water, or petroleum, oil products of some kind. And depending on where we are, the pore spaces could be full of any of those things. And that's an artesian well or a spring. And the other thing, the last thing I wanted to talk about is I want to revisit this drawing that I had at the very beginning of my level from Mario. You remember this one? So guess what? Sometimes, as I said, this actually does happen. Sometimes this does happen where it's not called an aquifer though. What is the right name for this? Can you guess? I'm drawing a specific rock around this. You know what rock I'm indicating here? Oh, no, it's not brick. It looks kind of like bricks. It's called limestone. This happens in limestone. What's special about limestone? Oh, I ran out of room is what's special about it. It's calcium carbonate. What's special about that? You remember from your last test maybe, from the beginning of the year when we did minerals. What's special about limestone? Yeah, say it. It dissolves in water. It dissolves in water. So sometimes this limestone, which can dissolve in water, the rock itself is impermeable. Limestone is impermeable, but it dissolves in water. And so if there's a little crack in it, the water flows into that crack and dissolves some of the limestone. And dissolves some of the limestone. And eventually, it dissolves enough of the limestone that we end up with this. What do we call this thing? This big old hole in the ground. You could fall in here. You could climb around in here. What? Okay, not quite yet. We're going to get there. Keep that word in your mind, though. What is this right now? Cave. Yep, a cave or a cavern. Okay, that's one of the main ways caves form. It's not the only way caves form, but it's one of the main ways caves form. If the rock is limestone, there are probably caves in it. And if the cave is in limestone, it formed in this way because limestone dissolves in water. Now, sometimes, maybe we build a parking lot up here. There's FERD F15000, there's some buildings. This gets kind of heavy. This is continually eroding away in here. What you see what's going to happen is the thing Maud said, which is what probably is going to happen. Eventually, heavier and heavier stuff up here, erosion occurring down here, what's going to happen? The whole thing is now a sinkhole. That's how sinkholes form. And I'll tell you that for free. That's how sinkholes form. I had a lot of fun doing this. Let's learn about the quadratic formula.